Thank you, Massimo, for the kind introduction, and thanks everyone for joining, and our Japanese colleagues and Professor Koshizuka for this very interesting history of, let's say, the moving particle simulation starting from university towards a product commercially available, and now a little bit my job will be to showcase the industrial application we see in Europe, showcasing an example that is a little bit distant and different from, like, let's say, 90% of the application we see Particleworks, so automotive sector. Right now, we will look at actually tool cooling simulation. So the idea is that we have a drill or a numerically controlled milling machine, for instance, and we want to understand how to better cool and guarantee that the insert that will, let's say, work on the piece, on the metal piece, can last longer and can be cooled in a better way. And I think this example is a very interesting one because it will showcase the combination of the features that were shown and that were implemented in the last few years. So I think moving particle simulation is very strong, it's meshless, it opens up simulation to a wider range of engineers, but when we start to consider also the couplings and the modules that are found in Particleworks, increasingly, we can see that we have tailor-made simulation for different kind of application, working with just one digital model. Okay, so here is the agenda. I will try to showcase really directly how the new feature can help in improving the simulation workflow and give more insights to engineers. So we will look at multi-resolution. So on the fluid phase, so here are 3 of the 4 modules that are in Particleworks. So moving particle simulation for liquids, FVM for air, it's one of the approach for air, and temperature solver or thermal solver, the CHT type of simulation. So in each one of them, we have new features, and I will try to show them in the best way possible. So here is just a quick another example of visualization of flow in this kind of application. So we are looking at a drilling application with some coolant injected inside the drill, and we'll go towards the end of the tip and exit from the side, so we can visualize the flow and understand the velocity and the pressure profiles that developed during such operation condition. This is just to introduce a bit the application. Again, as mentioned, those are the modules. We will not discuss powders. GranulWorks is a separate module that lets you also analyze the aeration module we saw previously. But yeah, this is just a summary. And coming to the same slide that was just presented, I will highlight what are the topics that I will touch on. Okay, so the coupling between moving particle, finite volume, and CHT, so thermal solver, both for fluid and solids. The multi-resolution, so the possibility to have smaller particle size in some areas, and we will see in this example where we applied. And the CHT multi-resolution, so the ability to control the grid on specific elements of the solid thermal solver. Quickly, here is an overview of 2 types of systems that we analyze with industry leaders in this sector. Nothing can be shown, let's say, publicly. So we have these 2 simplified models that showcase the general ideas. So in some cases, we want to look at rotating flow that can be affected by the tool movement. And in another case, here we see a tool that rotates and also translates towards the metal side and we have an injection of the coolant from the inner of the tool itself. And basically in the example I will show, we have some CHT cells in the insert area. So those are the boundary conditions, just to give you a little bit of a quick introduction on that. So as mentioned, the first advantage is, of course, to have a visualization of the flow and a quick feel on how the operating condition can impact the coolability, the coolant efficiency on the tool. Here we have 2 rotational speeds, and we can see that the flow is affected by the rotation of the tool, the centrifugal forces, and that can change the performance of the tool and also of the coolant. Here we have the average HTC mapped on the surface depending on the RPM conditions. So again, this is just regular features that were already present and available. So one of the first advantages is to introduce a multi-resolution region. We don't need to discretize the fluid everywhere with a very big, very small particle. So the idea could be to have this box in violet, and we can see that particles in that area are smaller, and more specifically, they are able to capture the flow inside the, let's say, tool, the piece of the tool that is active, and the handle of that element. So there is a screw, and there are some features of that insert that we want to more closely analyze in terms of flow patterns. So we can clearly see the effect of the box that is a little bit big, so you don't see all the box, but you see that inside here we have a smaller particle size, and we see that the flow is better captured. There is a flow that exits that area that is not captured with the bigger particle size. And this is visible especially in the video, so it's a little bit laggy. Maybe, yeah. I will stop it maybe just to help it. There are too many videos. Okay, but the idea is that you can hopefully see the different flow patterns that develop because of that interaction. And in general, what is very important is that at the end, if we map the HTC on that area, we can have a better visualization of the flow. And again, here is just shown on the insert, but also the screw, if mapped, can be, let's say, so we can understand the HTC on that element in a better way. Then showcasing a little bit the air side. As mentioned, we already had the opportunity to couple air with fluid via the FVM solver. Here we have the example. So we see the velocity profile that develops due to the splashed oil, and there is a fully coupled system between the fluid and the air phase. And here is you see the droplets that are ejected from the system and the clear influence on the air field and the reciprocal influence between them. And yesterday, but also today, we heard that now the finite volume method allows for a thermal analysis as well. So yeah, we had the example of the washing machine vapors presented also yesterday during our workshop. And on the right, we see the temperature in air. And it's very interesting because we also see like around the tool, so in this case, and also on the walls, there are higher temperature, because air in this case was initialized with a very low value, so I think 0 degree, it was just a boundary condition example. But you can see that the tool temperature influence in this simple example the air distribution, and we see it also here. So we see around the tool the air temperature that changes, and also the influence of the oil temperature on the air phase. And if we look now at the solid, we know that we can have a custom grid on the solid. So the idea is that, again, just to go back one step, we have the possibility to do thermal analysis in solids, so conjugated heat transfer, and we already were able to do so in previous version. Here is the example for this application. The idea was to understand how the temperature profile of the tool can change depending on the number of jets that we use to cool the tool. Okay, so and we can see that the tool, when interacting with the metal piece, will develop a certain amount of heat and a certain temperature profile, and when we apply the jet, that region is cooled very efficiently, but we have, of course, the distribution of temperature inside the tool that will slowly develop in a transient way. And the idea was, and here I'm referring to an already presented result from conference in Italy. The idea was, how can we optimize the use of oil and coolant and the jets distribution? And in the past, we heard about Gaspare Argento from Ducati Corse, how they were able to reduce the oil amount needed to achieve similar heat transfer capabilities. So going in the same direction, we try to understand how we could change or let's say distribute the coolant around the tool in order to have better temperature profile. And yeah, here it's shown very clearly that when we combine on the left the second jet, we have a better distribution inside the tool. And that directly we can see from the software, it's an output, a CSV from the software. We can monitor the average temperature, and we were able with the second jet to reduce by 20%. Going to the feature that I mentioned, so coming in this version, we have the possibility to define multi-grid. So in some areas of our domain, we can have a smaller discretization of the solid phase, both for fluid flow or thermal solver. In this case, we see for the end windings of an e-motor that we are able to define separate resolution for the housing and the coils. And that is very advantageous on the thermal solver, again, because it reduces by a factor of 10 the number of cells for the conjugated transfer analysis. And here is the example applied to our tool. So we can see that the screw here has a way better temperature profile inside, because we are discretizing that element and only that element with a smaller grid. And here we see the effect of rotational speed on the distribution of flow and also on the average temperature. I didn't plot it, the average temperature here, but we can clearly see that the rotational speed, of course, influence the amount of oil also that stagnates in the proximity of the tool. And we can see how also the flow rate at the entrance could impact the flow. And here is just an image showing that with the triple flow rate, we have actually a lot more flow towards the metal piece that we work on. And this is the temperature, this difference between the three cases. So, of course, when we increase the number of rotations, because we increase the number of interaction with the metal piece, we have higher temperatures, and we see this shift. And we could also observe some small variation in how the flow rate can impact the temperature profile. We can see the moving averages, and there are some degrees of differences between the, let's say, low and high flow rate condition. Just to conclude, here is a summary of all the feature and the direction we applied Particleworks in this sector. So we have really a combination of all the aspects discussed both on the theoretical and also on the product development part just before my speech. And yeah, it's a quick overview. It's one application that might be a little bit different from yours, but yeah, I just wanted to showcase how you can combine the different solvers and maybe give you some ideas for further simulation and design challenging. Thank you.